On December 2nd, 3 Atlas is venting methanol at almost unimaginable levels. Atlas remains wildly overactive compared to every standard comet model. It's still roaring with activity far from the Sun, carrying 2 razor-straight tails, including a sunward anti-tail, and losing mass at a rate that doesn't match the available surface area for sublimation. At the same time, the chemical fingerprint of Atlas has drifted far outside the Comet Handbook. Nickel, methanol and CO2 all appear in abnormal amounts. Its orbit lies almost perfectly aligned with the ecliptic plane, and the anti-tail has been confirmed by multiple independent telescopes. That combination has forced some scientists to seriously consider a CO2 thermal shield hypothesis, and even the possibility of technological influence hidden inside Atlas's structure. Zooming in the surface of Atlas shows hexagonal tiling, a glass-like protective layer, magnetic pulses repeating every 143 seconds, infrared oscillations on an 11-minute cycle, and a large internal cavity within the core. Right now, 3 Atlas displays an unusually rich abundance of methanol while water is almost absent, pushing the chemical structure of Atlas completely away from any comet we've seen before. 3 Atlas has changed dramatically since the day it was first discovered, and that raises a sharper question. Are these transformations quietly affecting our solar system and the surrounding cosmos? We're about to dive deeper into that question next. Three, Atlas should be a fading ember by now, a quiet comet slipping through deep space on exhausted fuel. Every textbook says that at this stage 3I Atlas drifts, cools and slowly disappears into the statistical background. 3I Atlas currently travels roughly 186 million miles from Earth, bathing in only a thin drizzle of solar energy. At that distance, standard comet models predict that exposed ices are nearly spent, the coma has collapsed, and activity falls silent. Observers instead report that 3 Atlas stays bright with a persistent coma that refuses to shrink or dissolve into darkness. Fresh images show jets and dust streaming away from 3 Atlas, as if Atlas was still charging inward toward the Sun. Energy balance calculations strain to reconcile the faint sunlight reaching 3 Atlas with the vigorous outgassing that continues to surround Atlas. Researchers adjust albedo values, tweak assumed spin rates, and experiment with hidden reservoirs of ice buried beneath the surface of Atlas. Each revision explains part of the excess brightness, yet 3I Atlas keeps returning more luminosity than conservative models are willing to grant. For many astronomers, 3I Atlas no longer feels like a simple data point, but a live stress test for comet theory in this strange chapter. Instead of quietly fading from the sky, Atlas sits in conference slides and late-night discussions, radiating a kind of intellectual discomfort. Every extra week of sustained activity from 3 Atlas whispers that familiar equations might be missing a term or several hidden terms. That whisper does not prove any exotic engine inside Atlas, but the anomaly forces the community to keep the case open. 3 Atlas becomes a standing question mark in the data, a reminder that even cold objects can behave unreasonably hot. The next step is to watch how Atlas throws material into space, because the pattern of those flows may speak louder than the brightness alone. From a distance, 3I Atlas looks almost theatrical, framed by 2 unnaturally straight beams of dust, cutting across the dark for any known comet. One tail stretches away from the Sun in the expected direction, while a second, the so-called anti-tail, leans back toward the light, as if refusing the usual rules. Observatories tracking 3 Atlas measure a primary tail that extends millions of miles downstream, yet still stays surprisingly thin instead of fanning outward in every processed frame. The anti-tail of Atlas remains shorter, but just as precise, hugging a straight path close to the orbital plane like a filament pinned on glass. Analysts find that the long tail of Atlas tends to be about 5 times the length of the anti-tail, a simple ratio that keeps reappearing in independent datasets. Typical comets develop broad curved tails that twist with changing solar wind, and viewing angle leaving photographers with shapes that rarely match from night to night seen from Earth-based observatories. 3I Atlas instead presents tails that resist blurring, kinking or drifting far from their razor-thin tracks, as if some invisible scaffold subtly maintained the layout. Perspective effects can sharpen the apparent structure, yet models that treat Atlas as an ordinary cloud of dust struggle once Earth moves and the disciplined lines barely relax. Even fine-tuned dust simulations reproduce only fragments of the symmetry seen around 3I Atlas, before dissolving into the usual fuzz and curvature. The impression many astronomers share is a quiet unease, because the pattern around At-Last feels more deliberate than chaotic whenever At-Last appears in data. Twin beams seem to bracket 3. At-Last like rails hinting at a guided motion rather than a casual spray of debris. That visual puzzle naturally leads investigators to ask how robust those streams must be to hold their form against solar pressure, setting up the next question in the chain for researchers following Atlas closely. The sunward tail of 3. Atlas looks wrong at first glance, pointing toward the star instead of away. To keep that narrow line aimed at the sun, material around Atlas must hold against continuous solar wind pressure. When those forces go into the equations, the required density for the antitail of 3 Atlas jumps to extreme values. The stream linked to Atlas would need to be many orders of magnitude denser than the surrounding flow, far beyond expectations. In standard models, grains leave a comet in a gentle spray spreading into a broad, flexible fan over time. Under that picture, any sunward feature near 3 Atlas should quickly bend, curl and smear into a soft arc under radiation pressure. Instead, images show a pencil-thin filament that keeps its direction toward the sun frame after frame, as though some scaffold were guiding Atlas. Even creative adjustments to grain size, charging or outgassing geometry have not produced a comparably sharp, enduring structure around 3 Atlas. Here the density paradox fully reveals itself, and Atlas begins to feel like a numeric challenge rather than a simple curiosity. The behaviour of the anti-tail suggests something more coherent and tightly bound than a casual plume of dust leaving Atlas. Researchers are left balancing uneasily between stretching existing comet physics and admitting that 3 Atlas may occupy a regime not yet mapped. That unresolved tension drives the investigation forward toward the next question: how much total mass at last can realistically afford to lose? Astronomers next turn from the elegant tales of Atlas to the hard accounting of mass. Brightness models implied that 3 Atlas was shedding hundreds of tons of material every second, a leak sustained over weeks and months. To check the numbers, researchers estimated the size of the solid core of Atlas from photometry and thermal data. Those measurements suggested a compact body with far less exposed surface area than the mass loss calculations seemed to demand. If all of that surface on 3 Atlas were actively venting gas and dust at reasonable speeds, the outflow would still fall short of the required total by a wide margin. The gap between available area and required throughput refused to close no matter how parameters around Atlas were stretched within plausible bounds. In familiar comets, such a mismatch usually signals an impending structural failure. Once enough material leaves the body tends to fracture, crumble, and spread into a cloud of rubble that rapidly dims. Instead, observations show Atlas holding together as a single coherent source, with no obvious swarm of fragments surrounding 3 Atlas. For an object apparently bleeding mass at this pace, Atlas looks uncomfortably intact. Some modelers propose buried reservoirs, narrow superactive vents, or unusually porous layers inside 3I Atlas to reconcile the contradiction. Others suggest that assumptions about grain size composition or thermal conductivity may be skewing the inferred loss rate around Atlas. Those ideas may eventually repair the books, yet for now the ledger on Atlas remains in the red. The more carefully the numbers are checked, the more 3 Atlas forces investigators to wonder whether standard comet physics is being pushed to explain behaviour that may belong in a different category. For many researchers, Atlas has become unsettling. That doubt becomes the bridge to the next anomaly, where the chemistry of Atlas begins to pull even further away from what models prefer. Spectra first treated Atlas as a routine confirmation step, another cold visitor in the log. The more carefully those spectra were stacked, however, the more 3I Atlas began to stand out from the archive. Lines that should have traced familiar mixtures of water vapour and carbon compounds behaved strangely around Atlas. Nickel features rose from the noise with unexpected strength, while signals linked to iron lagged far behind 3I Atlas. In standard cosmic environments, nickel and iron travel together, forged in the same stellar furnaces and mixed through the same collisions. When laboratory models tried to match the gas streaming from 3I Atlas, they ended up with blends that looked closer to engineered alloys than raw ore. Researchers hesitated to use that language in public, yet several teams privately described Atlas as chemically reminiscent of high-temperature shielding materials. The idea felt uncomfortable, but the numbers around Atlas refused to slide back into the safe zone of ordinary comet chemistry. Polarization measurements deepened the puzzle. Light scattered from the dust around 3 Atlas returned, with a negative polarization stronger than any value logged for solar system comets. The grains near Atlas behaved as though their shapes or coatings were tuned in ways that simple fluffy aggregates could not reproduce. Standard dust population models bent under iteration, yet the signature from Atlas kept its distinctive imprint. Mainstream comet scientists reminded everyone that the sample of confirmed interstellar comets was small. 3 Atlas did not cooperate. From that cautious point of view, 3 Atlas could represent a natural combination drawn from unfamiliar birthplaces. Still, the mix of nickel-heavy chemistry and extreme polarization made Atlas feel like a data point pulling on the edge of the map. For investigators following the case, 3 Atlas became less a curiosity and more a prompt to ask where the line between natural diversity and hidden design should be drawn next. Jupiter offers something that models alone cannot give a live experiment in the path of 3I Atlas. In March 2026, Atlas will pass the giant planet at a distance brushing the edge of Jupiter's hill sphere. That boundary marks where Jupiter's gravity seriously competes with the pull of the Sun on Atlas. If Atlas behaves like a conventional comet, the encounter should yield only small, predictable adjustments. For many researchers, this turning point around Atlas feels like a scheduled exam. Tiny shifts in speed and direction would follow well-understood equations as Jupiter tugs briefly on 3I Atlas and then releases Atlas into a slightly altered orbit. Simulations already trace conservative families of outcomes for Atlas. In those runs, 3 Atlas remains a passive stone responding but never misbehaving. The interest lies in what happens if reality steps away from those forecasts around Atlas. A modest but sharply timed change in course, or an energy gain that exceeds gravitational bookkeeping would hint that some other process is acting on 3I Atlas. Even a subtle deviation from the most probable corridor would force modelers to re-examine key assumptions they have layered onto Atlas so far. Observers are preparing for this flyby as a kind of cosmic audit, a moment when nature will grade every theory about 3I Atlas at once. For many of them, Atlas has become an open question written into the sky, and Jupiter will place the final mark on that question not with words but with motion. From the first precise orbit solutions 3. Atlas refused to behave like a casual passerby from the stars. The trajectory of Atlas did not slice randomly through the solar system, at some steep angle the way interstellar debris is usually expected to arrive. Instead, calculations showed 3 Atlas gliding almost perfectly within the flat plane where the major planets travel with only a slight remaining tilt. Dynamical models estimate that a random visitor has only about a 1 in 500 chance of aligning this well with the planetary plane. 3 Atlas therefore occupies a thin slice of probability space, where coincidence remains possible, but no longer feels comfortably anonymous. As observers added fresh astrometry, the refined orbit of Atlas stayed welded to that plane, instead of wandering as new data arrived. The story of 3 Atlas quietly shifted from a routine discovery note to an open question about aim. Some researchers argue that selection effects guide what gets noticed, and that Atlas could simply be the rare aligned case that finally stood out. Others point out that 3 Atlas races along at nearly 60 km per second, a speed that makes the clean alignment of Atlas resemble deliberate ballistics more than a thrown stone. Between those views, 3 Atlas becomes a fault line in the field, dividing those who lean on luck from those who suspect a pattern. That divide prepares the next line of inquiry testing whether the structures and behaviour surrounding Atlas truly support coincidence or quietly undermine it. When the first high-resolution images arrived, 3I Atlas stopped being an abstraction on a plot and became disturbingly precise. The Hubble Space Telescope caught a view of Atlas showing a narrow streak of material pointing almost directly toward the Sun, the opposite of what a comet tail should do, while a broader familiar tail of Atlas swept away from the star as expected. Skeptical voices suggested that perspective tricks or background stars might be confusing the picture around Atlas. Others proposed that unusual dust grains could line up just right, giving 3 Atlas the illusion of a solid anti-tail where none truly existed. For a brief time, the anomaly was filed under image processing glitches, something that might dissolve once more data on Atlas came in. August observations from the Keck-2 telescope in Hawaii refused to cooperate with that hope, and repeated the same geometry around 3I Atlas. Independent instruments and separate teams recovered the same sunward structure tracking alongside Atlas, leaving little room to blame a single detector or reduction pipeline. That confirmation shifted the tone of the conversation about Atlas. What began as a curious glitch turned into a stable, measurable anomaly pinned directly to 3I Atlas, which now carried one tail that obeyed the textbooks and a second that openly defied them, pushing investigators toward the next step, calculating what kind of environment or mechanism could keep such a sunward structure intact against the constant pressure of the solar wind. For many researchers, Atlas no longer looked like a simple comet. The spectrum of 3 Atlas started raising eyebrows before the striking tails did. Where most comets broadcast water and simple organics, the gas around Atlas spoke in a different accent. Nickel lines rose from the background while the usual iron companions near 3I Atlas stayed oddly faint. Because stellar furnaces forge nickel and iron together, the imbalance around Atlas became hard to ignore. Laboratory blends that tried to mimic the glow of 3 Atlas kept drifting toward alloys rather than raw ore. Ratios matching the emissions near Atlas resembled high-temperature nickel-rich materials more than untreated cosmic dust. Researchers avoided dramatic claims, yet internal comparisons likened 3 Atlas to engineered heat shields and turbine components. Public papers used cautious language even as the numbers for Atlas quietly repeated the same skewed composition. Supporters of a purely natural origin suggest that 3 Atlas formed in an extreme environment where metals separated in unusual ways. Skeptics reply that the selective enrichment around Atlas feels more like a deliberate signature than a random quirk. Between those positions, many investigators now file 3 Atlas under active investigation, and they turn next to the balance of ices and gases surrounding Atlas for independent confirmation. Observations of 3 Atlas showed that the gas surrounding Atlas carries a new and troubling physical imbalance. Instead of comparable amounts of carbon dioxide and water, Atlas displays a CO2 to H2O ratio near 8:1. Most comets sit close to 1:1 with only modest swings, nothing like the surplus measured for Atlas. That excess pushes 3 Atlas into formation scenarios far colder than the reservoirs that shaped familiar comets. Chemists place Atlas in remote nurseries at the edge of stellar systems where sunlight barely exists and reactions crawl. Even in those extreme settings, the mixture around Atlas presses against the limits of standard comet chemistry. Loeb and others respond with a hypothesis that carbon dioxide on Atlas may function as a thermal shield. In that picture, CO2 near 3I Atlas acts like ablative armour, boiling away and dragging heat from the surface. An interior structure inside Atlas would then remain cooler, protected during passages through harsher zones near stars. The idea is speculative, yet it forces scientists to treat Atlas as a potential mechanism rather than mere rubble. That tension between ice and shielding feeds the next key question: how 3I Atlas responds to heating. By this point, the scientific community has been forced to admit that 3I Atlas does not fit comfortably inside the standard comet box. Catalogues still list 3 Atlas as an interstellar comet, a natural body wandering through the solar system on a long arc from elsewhere. That label reflects a cautious majority view, one that prefers to treat Atlas as an exotic but ultimately natural outlier. The same consensus also accepts that 3 Atlas carries a precise orbital alignment, a confirmed sunward tail and a skewed chemical profile. Each feature around Atlas is logged as a curiosity, a challenge for future models rather than a sign of hidden design. In official language, 3I Atlas becomes a stress test for theories of comet formation and evolution, not a candidate artifact. A growing minority, however, argues that the pattern around 3I Atlas is too coherent to ignore as mere noise. To those researchers, the trajectory, the anti-tail, the nickel-rich chemistry, and the CO2 surplus form a chain of linked questions centered on Atlas. The disagreement is not only about data, but about how bold science should be when anomalies persist around a single object. At this scientific crossroads, 3 Atlas forces a choice between retreating into familiar explanations or openly testing more speculative hypotheses. Responsible skepticism does not mean refusing to ask whether Atlas could embody technology. Responsible skepticism means designing ways to check. In that sense, 3I Atlas becomes a mirror for the culture of science itself, reflecting courage, caution, and the limits of collective imagination. The next step is to look more closely at the surface and inner structure of Atlas to see whether the fine details support a strange natural history or something closer to a constructed mechanism. The first detailed reconstructions of 3 Atlas turned a distant point of light into a structured world. Instead of a rough, irregular lump, Atlas revealed ridges, arcs, and repeating curves across one hemisphere. brightness maps showed bands and nodes on 3 Atlas following paths that resembled contours on a circuit diagram. Shadows fell in patterns that hinted at terraces and channels, as though Atlas had been carved rather than shattered. Radar and photometric models outlined regions on 3I Atlas, where reflectivity jumped in discrete steps instead of sliding along smooth gradients. Along those boundaries, Atlas seemed to flip between darker and brighter zones, with unusual sharpness suggesting plates rather than loose debris. When researchers overlaid different viewing angles, key edges on 3I Atlas kept lining up, reinforcing the impression of a single underlying layout. Nobody can claim that these alignments prove design, yet the geometry around Atlas quietly resists the word accidental. For many observers, 3I Atlas evokes the feeling of looking at the underside of an unfamiliar machine full of seams, whose purposes remain hidden. That unease becomes the bridge to the next line of inquiry, whether the fields and forces around Atlas reveal rhythms that match the structured face 3. I Atlas shows in reflected light. Magnetic measurements near 3I Atlas began as routine background checks. Sensors around Mars and Earth logged faint field changes whenever their paths crossed Atlas. After weeks of collection, analysts noticed that the disturbances near 3I Atlas pulsed on schedule. Signals rose and fell with a steady rhythm close to 143 seconds. The period matched the measured rotation of 3I Atlas with striking stability. As Atlas moved deeper into sunlight, the pulses around Atlas strengthened instead of fading, as though tracking the changing energy. Standard explanations invoked patchy vents or cracking crust, yet those processes usually produce messy drifting signatures, not clean metronomes tied to Atlas. Surface studies added a different kind of structure. Reflectance maps showed regions on 3 Atlas rich in fused silicate glass not scattered in random patches, but spread as a thin, continuous skin. In engineering language, the outer layer of Atlas resembled a glazed coating, able to absorb and shed severe heat more like armour than dust. For several teams, the pairing of magnetic rhythm and glass shield makes 3 Atlas feel disturbingly deliberate, and that impression naturally leads to the next question, whether 3 Atlas simply survives its environment or can react to signals sent from ours. One experiment unsettled investigators by treating 3 Atlas not as a rock to be watched, but as a target to address. A low-frequency radio beam was aimed along the trajectory of Atlas. After a period of listening around 3 Atlas, a new pattern rose above the noise, a coherent echo from the direction of Atlas. Spectral analysis showed that the returning signal linked to 3 Atlas was not a simple reflection of the transmitted tone. Energy gathered into harmonics at intervals as though something near Atlas had reshaped the beam. Most strikingly, the modulation repeated on a 143-second cycle, the same period tied to the rotation and magnetic pulse of 3I Atlas. Engineers suspected side lobes instrument memory, or a delayed bounce from Earth's environment rather than any response from Atlas. Cross-checks with independent facilities failed to reproduce the pattern unless the beam passed near 3I Atlas. Nothing in the data proves that Atlas replied, yet the echo sits uneasily as pure chance. For many researchers, 3I Atlas now sits in an uneasy category, no longer only a visitor, but a possible participant, and that doubt leads into the search for internal power within Atlas. High-resolution radar reconstructions pulled back another layer of mystery from around 3I Atlas. Instead of mottled noise, returns from one hemisphere of Atlas traced a broad patch nearly 37 miles across. Within that patch, reflectivity maps on 3 Atlas broke into a mosaic of hexagonal tiles, each cell sharply bounded. Thermal overlays showed that several of those hexagons on Atlas ran warmer than their neighbours, forming a network of hotspots. Rather than a smooth gradient, the heat on 3I Atlas appeared in clustered nodes, as though channels beneath the tiles were carrying energy. Models that treated Atlas as a porous ice rock could not easily route power so precisely across the hex grid. Engineers recognised a familiar pattern when they studied 3I Atlas in this light. The layered structure and localised warmth resembled radiator panels or heat spreaders designed to move excess energy inside Atlas away from sensitive regions. The simplest explanation became uncomfortable: an internal power source within 3 Atlas, not enough to blaze but enough to hum. No one can yet say what mechanism might sit under those tiles on Atlas. Still, the combination of geometry and warmth pushes 3 Atlas further from the realm of random debris and sets the stage for the next clue: the mechanical vibrations and moving shadows that hint at motion deep within Atlas. Deep infrared observations added another strange layer around 3 Atlas. Sensors watching the thermal glow from Atlas picked up a faint but repeating fluctuation, as though some internal component was cycling on a schedule. The signal from 3 Atlas rose and fell every 11 minutes, too slow for simple rotation, and too fast for ordinary cooling. Instrument teams first suspected spacecraft artifacts, or background variability, not a true feature of Atlas. Cross-checks with different telescopes and nights, however, kept recovering the same 11-minute pulse tied to the position of 3I Atlas. The persistence forced analysts to treat the rhythm as a property of Atlas, rather than of the detectors. At the same time, stacked images revealed a migrating shadow near one polar region of 3 Atlas. The dark mark swung across a fixed path, vanishing and returning in step with the thermal cycle linked to Atlas. In natural terrain, shadows usually follow external lighting, not an internal timetable anchored to a single body like Atlas. Mechanical engineers looking at the data compared 3 Atlas to a machine with moving parts hidden behind a casing. From that perspective, the 11-minute cadence resembles a slow internal actuator or pump driving something inside Atlas. Nothing in the observations proves gears or pistons, yet 3 Atlas again behaves as though processes within Atlas obey a script. That impression leads directly to the question of structure, and whether the mass and layering of Atlas leave room for hollow spaces large enough to host such organised activity. Simulations based on radar density returns pulled back the outer shell of 3 Atlas in the most literal way. When researchers inverted those signals, they saw Atlas resolving into concentric layers, stacked one over another like armor plates. Each modelled shell within 3 Atlas came out denser and more heat-resistant than the one above, as though Atlas had been hardened from the outside inward on purpose. Between layers, the propagation speed of radar echoes suggested interfaces rather than gradual transitions, as if bonds inside Atlas changed abruptly at specific depths. That stepwise structure made 3I Atlas resemble a shielded vessel more than a frozen snowball. Instead of a uniform mix of ice and rock, Atlas looked like a nested system whose outer skin and deeper strata served different roles. Most unsettling was the void implied by the model. To match the observed mass and radar delays, 3I Atlas required a central cavity, occupying roughly 1/5 of the internal volume. The empty core inside Atlas did not behave like a random pocket or fracture. The shape came out smooth offset slightly from the geometric centre of Atlas in a way that hinted at design. One astrophysicist at a European agency remarked that 3 Atlas behaved less like a comet and more like a programmable object. That single word, programmable, spread quickly through informal discussions of Atlas. From then on, many teams began to ask whether the strange composition and rhythms of 3 Atlas might be features of a controlled system, not just side effects of a distant birth environment. Analysts next turned to the bulk makeup of 3 Atlas, asking how dense Atlas truly is beneath the layered shell. Gravity and motion constraints showed that Atlas outweighs expectations for an object of its size. 3 Atlas seems to carry more mass than standard mixtures of rock and volatile ices would predict. Spectral hints near specific lines suggest that matter around 3 Atlas may even include exotic metal hydrides. Those compounds, if present, usually demand pressures and fields found near neutron stars, not in a wandering body like Atlas. No one claims that 3 Atlas formed beside such monsters, yet the chemistry around Atlas keeps pointing toward extreme foundries. From these clues grew the resonance hypothesis. In that view, 3 Atlas maintains self-sustaining magnetic and electric fields, using dense material inside Atlas as a kind of circuit. Those internal fields could let Atlas tune its response to changing radiation, perhaps even soften forces that would otherwise tear Atlas apart. For investigators drawn to this picture, 3 Atlas becomes less a relic and more a participant, and the next step is to ask whether the heartbeat of Atlas lines up with any natural rhythm already known from our own planet. One more pattern pushes 3 Atlas into new territory, a pulse that seems to echo our planet. Analysts tracking faint field changes near Atlas keep finding a repeating interval of about 143 seconds. Converted into frequency, that rhythm from 3I Atlas falls inside the Schumann range where Earth's atmosphere resonates. Those Schumann modes arise from lightning strokes pinging between ground and ionosphere, forming a planetary heartbeat. When researchers overlay the spectra, the main peak from 3I Atlas sits close to Earth's fundamental resonance curve. Formal tests still allow coincidence, and no one can claim that 3I Atlas chose this band. Even so, the match nags at teams who stare at the plots traced back to Atlas night after night. For cautious minds, 3 Atlas simply radiates in a band that planets with thick air are equipped to notice. For bolder minds, Atlas begins to resemble a messenger tuned to worlds like ours. That possibility now colours the way investigators read the remaining chemical and dynamical anomalies tied to 3I Atlas. 3 Atlas first drew chemical attention when early spectra hinted at an unexpected alcohol haze. Follow-up observations confirmed that the gas around Atlas carries a strong signature of methanol. In most comets, methanol is a trace component beside dominant water vapour, yet around 3I Atlas the balance appears flipped. Water lines stay muted while methanol lines dominate a reversal that immediately marks Atlas as unusual. Modellers tried to place 3I Atlas in ultra-cold formation zones where carbon-rich ices condense more easily than water. To sustain the measured abundance, 3 Atlas must preserve large reservoirs of methanol, or release methanol far more efficiently than water from Atlas. This imbalance turns 3 Atlas into a contradiction for existing tables of comet compositions. Either Atlas passed through processes that strip water with surgical precision, or Atlas assembled from feedstock very different from the clouds that built local comets. For cautious researchers, 3 Atlas simply stretches the range of exotic but natural outcomes. For others, the scale of methanol excess feels like a deliberate accent, a chemical emphasis layered onto Atlas. That disagreement now feeds into the wider pattern of anomalies and sets up the next question whether 3I Atlas can still be reconciled with comet physics at all. Comet chemistry models were never built with 3I Atlas in mind. When researchers plug the measured ratios from 3 Atlas into standard reaction networks, the equations strain and feedback loops run away. Balanced solutions for Atlas often require parameters far outside laboratory ranges or demand reservoirs that contradict other observations. Some teams try to rescue familiar frameworks by placing 3I Atlas in extreme environments, such as ultra-cold outer disks. In those imagined nurseries, Atlas could in principle accumulate odd mixtures, yet the path still feels forced. Laboratory experiments recreating icy grains under those conditions rarely yield compositions that look anything like the spectrum of 3I Atlas. Again and again, the derived mixtures drift back toward water-rich blends while Atlas keeps pointing in a different direction. This tension does not prove that hidden engineering shaped 3I Atlas, but instead reveals uncharted corners of chemical space. Either Atlas encodes a natural history that current models have not yet imagined, or 3 Atlas reflects deliberate tuning of ingredients. For many investigators, the honest answer is that present theories are being pushed past their comfort zone by Atlas. That admission prepares the ground for the next challenge, the way 3 Atlas moves through space in ways that also quietly resist easy classification. Early orbit solutions hinted that 3I Atlas was not following a perfectly smooth gravitational arc. Residuals in the fit suggested a small but real deviation, as though something had nudged Atlas sideways for a moment. For a body moving at interstellar speeds, even a subtle change in course can carry large implications, and 3 Atlas was no exception. Teams first modelled the offset as a brief impulse, a short-lived push acting on Atlas over days rather than months. In that picture, a jet or concentrated plume from 3 Atlas could in theory supply the required momentum. However, when observers searched for clear asymmetric vents or sudden brightening, Atlas offered no simple smoking gun. Later refinements spread the same total acceleration over a longer interval, smoothing the anomaly around Atlas into a gentle non-gravitational term. With this adjustment, 3 Atlas slid back into the comet category on paper, driven by extended outgassing rather than a sharp kick. Critics of that approach argue that the behaviour of Atlas has been reinterpreted to fit expectations instead of letting the raw timing drive the story. For cautious minds, 3 Atlas may still be an ordinary comet whose quirks reflect measurement noise and evolving data. For uneasy minds, the way the anomaly around Atlas softens under reinterpretation feels like sanding down a warning sign. That discomfort now feeds directly into analysis of the upcoming encounter with Jupiter, where the orbit of 3I Atlas will be tested under a fresh and unforgiving gravitational lens. The planned flyby near Jupiter places 3I Atlas on the edge of an invisible boundary. That region the Hill sphere marks where Jupiter's gravity briefly rivals the Sun's pull on Atlas. In simulations, a passerby that grazes this zone experiences small changes, and 3I Atlas now approaches that test. Dynamical maps trace families of paths for Atlas showing how Jupiter might bend 3I Atlas. Across the centre of those maps, outcomes for Atlas look ordinary, with gentle deflections that fit standard expectations. Along thinner bands, the same encounter yields sharper shifts, forcing investigators to reconsider the forces on 3i Atlas. The key question is not whether Atlas comes near Jupiter, but how precisely 3i Atlas threads the threshold, where capture diversion and near miss separate. If chance alone guides Atlas, the flyby should fall somewhere in the middle of the prediction fan. If 3i Atlas instead passes through narrow corridors that maximize influence without binding, at last the geometry will feel closer to choreography than drift. For cautious analysts, the encounter will tighten the orbit solution of Atlas and file away a curiosity. For others watching 3i Atlas skim that gravitational edge will resemble witnessing a test flight, and whatever path emerges will move the story of Atlas from speculation toward verdict. Nickel and iron are usually born together in stars, so debris from those stars tends to keep both metals in step. That expectation makes the spectra of 3i Atlas hard to ignore. Across independent campaigns, the nickel lines tied to Atlas rise cleanly above the iron features, while iron stays muted. Dust and gas models cannot easily push 3i Atlas this far toward nickel without dragging iron along. When researchers force the match, the mixtures around Atlas begin to resemble selectively refined material, rather than the blended rubble of a shattered world. One family of scenarios imagines that 3i Atlas once struck a metallic body, stripping away ordinary crust and leaving a nickel-rich envelope around Atlas. None of these sketches rise beyond hypothesis, but each one concedes that 3i Atlas will not follow the standard metal ratios. For cautious voices, Atlas remains an exotic natural remnant from a harsh and unfamiliar nursery. For uneasy voices, the nickel emphasis around 3, Atlas feels less like a random quirk, and more like a hint of deliberate tuning. Either way, the imbalance adds another stone to the growing pattern, nudging Atlas further from simple labels and toward a closing question about what all of the anomalies around 3i Atlas may have in common. Taken one by one, the puzzles around 3i Atlas might pass as curiosities in a noisy universe. Seen together, they form a pattern that resists classifying Atlas as an ordinary comet. Observers log the precise orbital alignment of 3i Atlas, the sunward tail, the nickel-rich and methanol-heavy chemistry and the layered shell with a hollow core. Modelers then fold in the rhythmic pulses tied to rotation of Atlas and to Schumann-like bands along with non-standard metal ratios and strong polarization linked to Atlas. No single measurement screams artifact, yet the full set keeps pushing against the limits of every natural model built for Atlas so far. Attempts to fold 3i Atlas back into standard comet theory demand fine-tuning rare environments or generous luck applied repeatedly to Atlas. From one angle, this simply means our theories are incomplete, and that Atlas occupies a corner of parameter space we have not charted yet. From another, the same data make 3i Atlas resemble a mechanism whose purpose we do not yet recognize, a tool drifting in debris fields. Scientists committed to caution stress that extraordinary claims require extraordinary evidence, and that Atlas has not crossed that line. Scientists drawn to bold inference answer that never testing technological hypotheses for 3, Atlas would be its own unscientific bias. For now, 3i Atlas forces both camps to design sharper observations and stricter simulations, and future encounters, especially with Jupiter, will either pull Atlas toward familiar categories or push 3i Atlas deeper into mystery. For now, 3 Atlas hangs in our sky not as an answer but as a carefully framed question. Every time a new dataset arrives, Atlas either stretches existing theories or exposes fresh seams where comfort once lived. We have measured the brightness of 3i Atlas, the tails, the chemistry, the pulses, and the hidden cavity. Each of those pieces could in isolation be folded back into chance, yet together they surround Atlas with a persistent outline. That outline does not prove design, but 3i Atlas keeps behaving like a prompt asking how far curiosity is willing to go. Some scientists look at 3i Atlas and see a laboratory of extreme natural processes, a place to test the edges of cosmology. Others see a possible artifact wrapped in dust, a mechanism that crossed light years before brushing our small circle of planets. Between those poles, Atlas becomes a mirror reflecting our habits, our fears, and our willingness to question even our own skepticism. The upcoming passage by Jupiter will not settle everything about 3i Atlas, yet the maneuver will mark a decisive chapter. If the motion of Atlas and the changes in activity behave exactly as conservative models predict, relief will spread quietly. In that case, 3i Atlas will still be strange, but strange in a way that invites new natural stories. If the path of 3i Atlas jumps the tracks even slightly, the comfort will evaporate. An unexpected gain in energy, a sharper turn than gravity allows, or a renewed burst of structured activity would move at last into a different category. From that moment, the burden would shift, and those who dismiss technological hypotheses for 3E at last would need firmer reasons than habit. Whatever future the data delivers, 3 at last has already changed the conversation. At last has forced astronomers, engineers and philosophers to stand in the same room and admit how much remains unknown. At last has reminded everyone that absence of evidence is not evidence of absence, but also that untested ideas are not evidence either. In the end, the true power of 3 at last may lie less in what at last is, and more in what at last makes us do. 3 at last pushes us to build better instruments, to share data more openly, and to confront our own confirmation biases. Whether future generations remember at last as a bizarre comet, or as the first recognised mechanism from another star, one fact will remain. For a brief moment in cosmic time, 3 at last asked humanity a simple, relentless question. Were we really paying attention? Long after 3 at last has left the reach of our best instruments, its data will remain. Those traces will sit in archives awaiting fresh eyes long after the first generation of at last investigators is gone. A student not yet born today may reopen the files and see a new pattern in at last. Perhaps by then our technology will allow a follow-up mission chasing where 3i at last once travelled. Or perhaps we will recognise similar signatures elsewhere, and at last will become the template that taught us how to notice. Whatever the outcome, 3i at last has already done something remarkable.